Okay, right. So this is almost last lesson, last official lesson, and yeah, we're going to learn about the problem of today, of this year, really, in graph theory, and that's the traveling salesman. What we learned last time, the algorithm of finding a minimum spanning tree, is just going to help us to solve this problem. So I mentioned this problem last time. We've got cities, okay, A, B, C, D, E, E, F, okay. Each one of these vertices is a city. We've got the edges, which can be the parts. Obviously, that's just one example. It could mean many other things. But originally, that's how this problem was posed. And a specific person, a salesman, is coming out from one specific place. In this example, we identify the E as the office. So he starts from here. He has to go through each one of the vertices, each one of the cities, okay, and then come back to the office in the shortest route. So he doesn't have to go through all the edges, okay? He has to cover all the vertices. That's a Hamiltonian circuit rather than an Eulerian circuit, if you remember that from last year. So how do we know it? So interesting to say, first of all, that there is no algorithm for that. So we don't actually have, or there is not known algorithm to solve this problem. So, I mean, this is a small graph, okay? We can just by trial and error go for a few and we'll find which one is the shortest. But if you have, imagine even if you just have 20 vertices, it's going to be, I mean, even a computer will take forever to go through all of them. So until today, there is not a known algorithm to find the optimum solution. So what we're looking for is, yes, I'm just going to pause here. Right. So yeah, there's no known algorithm to find the optimum solution. So what we're looking for is bounds, higher bound and the lower bound. And I'll explain what these mean. So we're going to have a higher bound. I'll write it down here. Higher bound, and a lower bound. Okay. The solutions will exist between those bounds, and the closer we get to the lower bound, or the closer we get the higher bound to the lower bound, the more we know we're getting a closer solution, the better solution. So what we do have are algorithms to find the higher bound and the lower bound. Okay, we'll start with the lower bound. So to find the lower bound, essentially what we do is we remove one vertice, okay, and I'm just following the example, but it can, they got rid of D. We're going to get rid of D, get rid of one vertex, and then find the spanning tree for the rest of the vertices, okay, which is what we learned last time, okay, and then once we found the spanning tree for all the rest of the vertices, then connect that tree to D through two edges, shortest edges. It sounds complicated, it isn't, it really isn't, okay? So let's just write it down. I'll write it down, then we'll go through it. Right, so here's our first algorithm, or only algorithm to find the lower bound, okay? Step one, remove a vertex. It could be anyone, we decide to remove D. Step two, create a spanning tree, okay? So let's create a spanning tree of the rest. Let's use Kruskal, okay? Just to kind of remind us how to do it. You can do it Kruskal or Prim, okay? Kruskal, what does Kruskal tell us? Choose the shortest, the smallest edge. I'll need you here, Olivia, to remind me, okay? So 35 is the smallest one, yeah, right? And then just add them up all the time. Higher. Don't make a circuit, okay? And then until maybe we can count first and to know how many edges we need. So we don't count that one. So 1, 2, 3, 4, 5 vertices. So we need 4 edges. Okay? Right, so 35. After that, I've got a 40. I've got 2 40s, but hang on, this 40 goes to the D, so I don't need him. Because he's not in the spanning tree, so it's going to be that one. Then 50. It's kind of like, what do you call it? You know what I'm talking about. Anyone in 45? Do you have anyone for 45? 50, 55. Okay,
Like
what do you call this?
It's an auction.
It's an auction.
So you go 55.
I never thought about 40. Anyone for 45? 45.
No,
Not anyone for 45. 50. Okay, 50. We got 250. Which one do we take? You take any one you want. Let's take that.
Oh yeah, you can.
Actually, we don't want that
No,
one.
you can't take that one.
We don't need it because he's not in the tree.
But you can start anywhere.
And yes, cruise school is all over the
Yeah,
place.
okay.
Cruise school prim, only where you touch
Yeah.
it. You touch. Okay. 50. Okay. 55. No, because he's there. 60. Anyone for?
55.
Hang on. 55. But it's a circuit.
So you can't do it.
So we don't want to do that. If we do that, we're not achieving anything because we touched C, we touched A. It's not gonna.
So
we
then
don't even.
60.
So 60 to be able now to get F under control.
And
And
that's
now
it.
we've got 1, 2, 3, 4. Everyone's touching.
Okay.
Touching. Not there yet. Okay. So we've done step 1. We've done step 2. Okay. Now what we're gonna do is just connect D to the spanning tree through 2. So we're not doing a span. Otherwise, I mean, if we're connecting through one edge, then they might as well just tell us find spanning tree for all of them. No, but we need 2. Okay. So, but the 2 shortest one. So I guess that will be 40 and 50.
Yeah.
Yeah. Okay. So now we're reconnecting him. Okay. And we're gonna connect here and
Because
here.
now you've been to all the vertices.
I've been to all the
But
vertices.
you want to end it either.
Let me just explain that. There is an issue here, but let's just pause and add them all up. So what we need to do now is just add them all up. Okay? I'll pause, we'll do it, and we'll come with a number and then explain what we actually achieved. Okay, so I've added up all these edges, and what I got is 275. Now, lower bound. I used to call that the minimum, but then I read now here, they don't like minimum, and that's good, because the thing is, you see, the lower bound is a theoretical figure. It doesn't mean that there actually is a root.
Yeah, because it's not back to the beginning.
Exactly. So this doesn't guarantee that there is a root that is 275. What the lower bound theoretical lower bound means that you will not find the root that is smaller than 275. The smallest that you might find, you might not. They might not exist 275, but you're not going to find anything smaller. And in this case, if you look at all the edges that we've done, okay, it's not just that we didn't go back to where we started from. I mean, this is, you know, I need to go through one of those twice. Like, I can go like this maybe, but then I still need to go back here. So these paths, I will have to go through some of them twice, you know? Even if, let's say, I wanted to start and end at D, okay? So, okay, all right, I got that, but then I'm going to have to go through it back. Okay, you understand what I'm saying? So it's not guaranteed. The theoretical lower bound is not guaranteed, but you'll never find something smaller than that. So what we got to do now is be able to find the higher bound. And the higher bound already going to tell you now, it's an not experimental, I'll use empirical. It's an empirical number. That means it's one that we definitely find. Okay. And essentially the idea is that I will show you an algorithm that helps us find one, and we just find one, and the one we find is our higher bound. There's probably are lower than this, so we just gotta do it again and again, and hopefully we find something that is a bit lower than the higher bound. What's the theoretical lower bound for? The closer we get to it, the more we understand that, okay, you know, we might get close to it will be a good solution. In other words, the smaller the difference between these bounds, the more confident we can feel about our solution. Okay? Right, I'll pause, make some space. Okay, so I've got back we drew the same circuit. We established that the theoretical lowest bound, we can't go lower than that. We're not going to find a solution that is less than 275, but it doesn't mean necessarily that we have a solution that is 275. So now we're trying to find the highest bound. The highest bound is basically your best solution so far. Okay? And I mean, you can just try different things, but computers can't just try different things. So we got to give them a step-by-step solution, and we call that an algorithm. And this specific algorithm is called the nearest neighbor solution. Step 1, pick a vertex. Okay? Right? Now, the vertex that you need to start with really should always be the vertex that, well, depends. I mean, If it's a salesman that's got an office, he has to leave from somewhere. If the problem specifies where you have to start and where you end, then you got to go with that. If it doesn't, maybe you can just be anywhere you want, then you can choose anywhere you want. But in this case, normally I think they will specify where to start. In this case, they want us to start with E. Pick a vertex set to current vertex. Okay, so that's our current vertex right now. I'm going to draw in blue. Okay, just to know where we are. It actually makes a lot of sense, this algorithm. Step 2, find an edge which connects current vertex, the one in blue, to an unvisited vertex, which we call V. Okay, now it tells us, I'm just going to pause here for a second. Yeah, I thought I missed a word here. Obviously, we're not going to find any edge. We'll find the lowest edge, which connect our current vertex to a vertex which is unvisited. A neighboring is unvisited. So I can't just go anywhere. It's not crucial, it's more like prim. Okay, so I have 3 options, 55, 90, 50. We go with 50, right? So, right, so I'm choosing the 50. What's step 3 mean? Okay, then if I chose this 50 edge, now my current vertex is going to be now the next one, which is F in this case. So if I chose, it makes sense. If I chose to go on this road, now I'm in this city. Okay? Next thing, and what I'm going to do is also make a little arrow, because that's going to help us eventually trace the path that we went. Because when they ask us the question to find out eventually what's the circuit, it's not enough just to add up all the numbers, the distance. I also need to say what is the direction, what's the order. Okay, so it's good to put a little arrow here. Okay, now from F, now I need to carry on. Repeat step 2, step 3, carry on until all the vertices are being visited. Okay, so from F, makes sense. From F, where would I go? I can either go to B. B is shortest one, right? Okay, so I'm going to go there. Painted that one. Okay, got to B. Okay, from B, I'm going to go to A, I guess, because that's the lowest one.
Yeah.
Okay, and I'm putting an arrow. A, well, I visited the F anyway, so there's no point. So we're going to go to C. It's also lower anyway. C. Okay, the only one I'm missing now, I'm not missing, the only one I mean, obviously to B is quicker, but I don't want to go to D. I want to visit D. Okay? Sometime you might, and it's not officially there, sometime you might want to do a bit of a Gicastra. I don't know if you remember Gicastra from last year. So the Gicastra is, how do I go from one vertex to another vertex in the shortest path?
Oh, so you might go back if it's shorter. Yeah.
So for example, okay, in this case I should go to D. Okay, I will go to D. But what happened if this was, let's say, 5?
Yeah.
If this was 5 instead of 40, then actually I should go back to B and go to D through here. Okay. So, you know, when it's small little thing like that, you can think out of the box a little bit. We're better than computers in that way. Okay? Right, so we went to step 4. Carry on until all vertices have visited. Okay, they're all been visited. What do I do now? What should I do now? No, but I'm here. I need to go home. Go back home in the shortest way. So even here, maybe you'll have to do a bit of a Gicastra. Okay? You might have to actually go through here if it makes sense. Obviously here it doesn't. Okay? So that's it. Okay, so I'm going to pause now and add them all up. So I've added them all up, all these numbers, and what I've got is 305. Okay? Also, when they ask you these questions, they probably will also ask you the circuit that you're going to go. So you got to write it down like this. E to F to E to F to B to A to C to D back to E. You're going to end up with where you started. Okay? Now finally, let's just have a look at what's, look at these things to make sure we understand. Okay? And I will pause here a little bit. Okay, all good. Camera is working. All right. So let's just recap what we've done. Okay, we had the problem. Okay, first of all, we're trying to find the theoretical lower bound, the smallest possible solution that we can have, not guaranteed. We use a spanning tree. Let's write it down. So we use the spanning tree, minimum spanning tree. Okay. We had to remove one, well, I'm not going to repeat into it, but minimum spanning tree by removing one vertex and connecting it eventually later. Then, okay, we use the nearest neighbor algorithm to find a real, what I call empirical solution, okay, which we call, at this point, this is our highest bound. Okay? Now, we could try again. We could try, for example, maybe we can say, if we're not restricted by E, you know, maybe we can start from if, or let's say, maybe if we start from D, okay, if we start, for example, if we were allowed to start and end here, then you can already see that you're going to have something else. You're going to go from D to B, right? And then from to A, and then maybe, yeah, I don't know, okay? So where you start will give you a different different chain of events. Even more than that, okay? This nearest neighbor algorithm does not guarantee that it's going to be the best solution. What do I mean? Every time we always chose the shortest one. But who knows, maybe by going from here to actually to D, it might make it, maybe from here, then we'll go to B through here. Look at, yeah, so maybe, I don't know, yeah, I mean, look at this. If I go in from here, instead of going to F, I would go to D, okay? That's a bit longer than that. But then, instead of going to C like that, I will go to here, hit the B, and hit the C. So, I'm not saying it's better, but the main thing, this does not guarantee the best solution. So we're just going to do it again and again and again, okay? And the closer these bounds are to each other, the more confident we have that we have a solution, okay? If I do it, let's say, and just I'll finish here. If I do it again, start from a different point, or maybe instead of going to F, just try going to D. Let's say we get a solution now that is 290. Well, in that case, our higher bound now is 290. Every time we update the higher bound. Okay, I'll pause here. So, Olivia is asking, this distance, let's say I found another one and it's 290. Let's say. So now this difference between the lower and the higher bound is 25. What does that mean? Well, I don't know. There's no guarantee. I mean, there's only one possibility when there is a guarantee. If you suddenly got lucky and you found a higher bound, which is 275, then you're done. There's nothing. Okay? But, if it's 25, you don't know. You can try a bit more. Maybe work another hour or two and nothing happens. So, it's